All right, we're going to begin into a new topic, and it's going to span one of our last big topics that we will get into this semester. We're going to start talking about numerical integration, but I'd like to start with the question of why, um, because I like to motivate pretty much everything I do. I want you to understand there's a reason that we might be interested in doing some of the things that we're doing. One of the reasons that numerical integration is really important is because sometimes there are literally integrals that don't have a closed form solution, right? If you remember what an integral is saying, it's basically an inverse problem that's saying, um, what function would you need to take the derivative of in order to get this expression, this integrand? Sometimes there is nothing that we can write down using basic functions that can express this thing. And that's true even if a function is integrable. You might remember from first year that, right, differentiability implies continuity, and continuity implies integrability. But just because a function is integrable doesn't mean that we can find an antiderivative using simple functions that we can write down. And that's a little bit mind-blowing. So I want to talk a little bit about special functions to begin with, to just kind of show you about some of these more interesting, more exotic functions that can still be useful, that can still hold lots of information, and that we can still work with, even if we can't write them down. I think it's really fascinating. I hope you enjoy the lecture, and we should get started with it. So, as I said, we call these things special functions because they're just that special, I guess. I don't know. Given combinations of basic functions, there's always a step-by-step process for how to differentiate a function, assuming that it has like a lot of the basic properties that we come to hold for granted in a lot of the standard functions that we work with. And we would use derivative rules that you would learn at the end of high school or in first year. Even if the result is complicated, it's always straightforward to get to the results we need. We follow the step-by-step approach to find the derivative of a function. But integration is not the same, right? Usually, I when I teach first year calculus, I talk about integration as more of a puzzle, right? You're trying to use some sort of creativity, some sort of your knowledge about how derivatives work, and trying to piece together a suitable answer. You need some ingenuity to get there. Sometimes, though, an integral is actually impossible to solve, at least to write down. So there does not exist a combination of basic functions whose derivative is equal to a given integrand, kind of how I was speaking about when I opened up this lecture here. Functions like these are often called special functions, and even though they can't be written down explicitly, they're still quite important, and we can still extract lots of information. We can still analyze its behavior. We can do all sorts of things with these functions, even if we can't write them down the way that we might want to. And that's an interesting thing. And a lot of these functions will come up in higher level math and physics courses, maybe even some chemistry, engineering, and stuff like that. These functions are important. And so I want to talk about them. So I want you to consider this integral right here. It's the integral from a to b of e to the minus x squared dx. This integrand is continuous for all real numbers, right? If I look at this function, I could graph it. You could go to, maybe you don't know what it looks like offhand, but you could go and graph it on a graphing calculator or some other software. It's not too bad though. It's going to behave kind of like an exponential function that's mirrored on one side because the right, what's in the exponent there is going to be at least 0, right? Minus 0, and then it's a parabola on both sides. So what happens on one side will have to happen on the other. It has to be symmetric about x equals 0. And then we're going to get increasingly negative numbers on each side. So I'm expecting something that's sort of bell curve shaped, right? Because exponentials to negative numbers like shoot downward towards 0. And it's going to happen symmetrically on each side. So I'm expecting something that looks like this. Anyway, from first year calculus, I know that that integrand is continuous, and continuity implies integrability. And so this integral is well defined for any choice of a and b that we like. Right? Like we can find the area under this function. That makes a lot of sense, right? If we have this function that's continuous, I should be able to say there is a well-defined area under that function between any two numbers a and b. And yet, there does not exist any antiderivative for this function, despite that. And that's annoying, right? I think it's annoying at first because you want to say if that area is well-defined, if that integral makes perfect sense, why can't we write it down? Why can't we write down an expression for the area? There does not exist any antiderivative for this function. There's literally no quantity, I dare you to try, that if I differentiate it, I get e to the minus x squared. You know, you could try all you like to write things like, oh, it's just e to the minus x squared and, I don't know, an x cubed over 3 out front. And then you remember that if I took the derivative of this, I have to use product rule, and it's going to be way more complicated than e to the minus x squared. This isn't going to work at all, right? There's nothing that works. There's no combination, no matter how long you try, that will work. This is not something that I'm like saying we think this. It's true. It's a fact. Pretty sure people proved it long ago. Anyway, this integral comes up very often, no matter what, however, in statistics. And in fact, it was common enough, this integral from a to b of e to the minus x squared, was given a name because it does come up fairly often. It's nice to have a name to refer to it. The name is, however, a little bit confusing given some of our other numerical methods terminology. I mean, you'll see why. It's called the error function. Let's talk about this for a second. We have expressions for absolute error. We have expressions for relative error. We talked about error terms associated with the Taylor polynomial. We're talking about error all the time. And here I'm saying, this is an error function. This has nothing to do with the error that we've calculated in the past. It's just the name that was given to the function. Sorry. But here's what it is. You'll notice that this integral seems really familiar. It's the one that we were just talking about. We have a specific a and b value, 0 to x, whatever x is, and we have this scaling factor in front of 2 over root pi. So, okay, this is a function of x, not t. Here's why. Because if I was to find the antiderivative using like fundamental theorem of calculus stuff, I'm taking that expression, whatever it is, popping in a value of x and popping in a value of 0. Whatever this evaluates to ends up being a function of x by virtue of the fact that x appears in the bounds of integration. Okay, so there's no t in the end. T is like a dummy variable. And ultimately, we have a function of x that's going to be determined by how big or what position that x is. And what this does is essentially give me some sort of scaled amount of area under this function, right? The area between 0 and x, whatever it is, positive or negative, under this e to the minus t squared function, and then multiplied by some factor up front, for a reason that I'll kind of skirt over in a little bit. This is how the error function is described, and we're going to work with this for the rest of this lecture. Let's break down this function by first looking at the function in the integrand. So first of all, it's an exponential, e to the minus t squared. E to the anything is positive, and so that's just a fact. We know that even though we don't know anything about this integral, we've already identified that the integrand is always positive. Okay, the function is at its highest at t equals 0 and tapers off in each direction symmetrically. I kind of talked about that before, but try to plug in different values. E to the 0 is 1, so that's where it's going to be at its highest. And if you plug in greater values of t, positive or negative, you're going to get minus a smaller number, minus ever increasing numbers rather, and e to the negative huge goes to 0. So it has to taper off in both directions. Okay, and so that's the thing. The function must tend towards 0 in height in each direction. So this here is the graph of e to the minus t squared. This is not our function, right? This is a graph of the integrand only. So a graph of our integrand. And what we're trying to do is figure out something about the whole function. So we need to think about what the graph of the integral of this thing will look like. And that's an interesting problem. Okay, so back to our integral. Our integral is 2 over root pi times the integral from 0 to x of this e to the minus t squared. So we need to take this thing and we need to look at it and think of how, what the integral does to this. Like, why do we get to something interesting, right? It's a function of x, as I mentioned before. To come up with a graph of this function, we have to see how this function would change with different values of x, right? So just imagine, if x is equal to 0, for example, then this is an integral from 0 to 0, multiplied by some stuff. And we know all about integrals from a number all the way up to the same number. There's no area there. So that would have to give us 0. If that number, if the x here was 1, this would give me the area under the function from 0 to 1. And it's this positive area right here. And then we would multiply by this 2 over root pi. Right? If it was a negative number there, then we're going from an integral from 0 to negative 1. We're integrating backwards. So we add up we add up our areas negatively. We end up with some sort of negative answer. So it's this kind of thinking that's going to get us to the right thing. So the only place that this function could be equal to 0, as I said, was x equals 0, since the integral from a up until the same point a is always equal to 0, so no problem there. The integrand's always positive, and we're adding up positive area as x increases, but less and less as x goes to infinity, as the integrand does tend towards 0. So imagine, what I'm trying to say there is, imagine if we plugged x in, back in this graph, and I'm integrating from 0 up until x. If x was 1, I'm going to get this amount of area, and that's going to be what the integral gives us. If I instead plug in x equals 1.5, I get this additional area on top of what I had. And that's got to be the value of this error function thing. And if I put in x equals 2 into the function, I'm getting this whole area all the way up until 2, multiplied by that factor, and so on. I'm getting bigger and bigger amounts. This function's always positive, so as x increases, I'm always adding up extra area. The integral of that function must also be increasing. But it's got to be increasing less and less, because as I increase the x values here, or as I increase, the place where I'm cutting off the area 0 to x, there's less and less area that's being added as we go forward. So we're expecting an increasing function as x increases, reflecting the fact that we would get less and less and less area at the higher the x gets, but it would be increasing. Similarly, and this gets a little bit tough, for negative values of x, then we'd be integrating backwards. We're going from 0 up until a number that was before it. And thinking back to your conversations from Riemann sums in the first year courses and basic integration properties, if you're integrating from a value to a value that was before it, you're kind of adding up negative area, and you get to a negative value. And similarly, those are going to add up in one direction as well, and things are going to be basically, if I'm at it, so suppose that x was negative 1. Right? I get a total amount of negative area that's right here, and I'm going to get a negative number at x equals minus 1 for the function. And if my x was something even less than minus 1, I'm going to have more negative area, but less and less of that negative area is being added. So I'm gonna have a function that's negative, reaching 0 finally at x equals 0 when the integral goes between 0 and 0, and then increasing from there on, but maybe increasing less and less as x goes to infinity, and maybe there isn't much area that would be added on here negatively as x gets very big and negative. So maybe it comes up from being not adding very much of this stuff and comes in quicker and quicker as we come in towards 0. So some things to think about there, but it's all based on this graph. The last thing is that scaling factor, that 2 over root pi. And basically what that does is it ensures that the numbers end up nice. What this does is actually ensure that the height of the graph approaches plus or minus 1 at the end of the day, as x goes to plus or minus infinity. This is what it looks like. So we have horizontal asymptotes. Oops, right here. This is supposed to be a horizontal asymptote of y equals 1, and a horizontal asymptote here of y equals minus 1. And this is a graph that we could produce simply by observing what that exponential is doing inside the integral. So I don't even know how to write down the basic function, but I can still come up with all of this stuff simply based on observing things, by knowing something about integration rules, and integration properties, right? Really interesting stuff that we can come up with this. This here is the graph of the error function of x, which is that 2 over root pi integral from 0 to x of e to the minus t squared dt. Again, don't focus on the t. What you're caring about is the bounds and how right, it's talking about how much area is under this e to the minus t squared curve, depending on what the value of x is up here. So yeah, the error function is widely used in statistics because it goes really well with the idea of like, okay, the e to the minus t squared looks a lot like a bell curve, which is something that can occur a lot in stats. And this function here goes really well with, like, well, adding up areas, kind of like accumulating the amount of area that appears under that curve, which is then something that's associated with a cumulative probability distribution if you have that little bit of information from a stats course in your past. And based on all of our conversations, we can actually deduce some really cool properties. So the function here is differentiable everywhere. And the derivative of this function, imagine taking the derivative of that integral, you get nothing more than 2 over root pi e to the minus x squared. I do believe. Yeah, that's what it is. Because all you're doing is taking off the integral. That scaling factor remains out in place. And so we have a new derivative property of this bizarre function. Even though we can't write down the function, we know what its derivative is. Isn't that cool? I don't know. The limit as x approaches plus or minus infinity, of course, is plus or minus 1. Plus 1 goes with plus infinity. Minus 1 goes with minus infinity. Another really funky property, and you can see it quite easily in the graph there, is that this function, ERF of x, sometimes I'll say ERF of x, but it sounds kind of like you're trying to, I don't know, you ate some bad tacos last night and you're like, ERF of x. Or whatever. It's an odd function. And not only is it strange, but it's also odd. But that just simply means that ERF of minus x is the same as minus the error function at x for every value of x in the domain. So that's kind of cool. We have all of these different properties plus the graph, and we still don't even know how to write down the function, and that's pretty cool. That's to teach a bit of a lesson, right? That despite the fact that we can't write down that function, that doesn't mean we can't work with it and gain information from it, and maybe even use it to model different things, and to be involved. Like, we have a derivative, for heaven's sakes. This thing could be involved in a differential equation, for goodness sake. It's pretty interesting. And in fact, like many special functions, and like most not so special functions, it actually has its own Taylor series. And so we're actually going to work with this in a last example here. I think this is the last thing that we want. Yeah, I have a bit of notes before, but we're going to actually find the Taylor series for this function, which is kind of cool because if you think about it, that means that without knowing what the function is or being able to write it down other than an integral, we can still find a Taylor polynomial for it. And that's just really awesome. I don't know. I think it's really cool. So by manipulating the Taylor series for a related function, find at least the first four terms of the Taylor series for y equals erf of x. So I'm going to write a couple things down here. Let's just remind ourselves of what this thing is. This is 2 over root pi times the integral from, what was it again? 0 to x of e to the minus t squared dt. I'm just going to put this off to the side, and I want to think about constructing this function, a Taylor series for this function, out of one that we know. And if you think about it, if I start with the inside and work my way out, I know something about an exponential function, right? So that's where we're going to start. So the Taylor series. I'm not going to do anything special here. The Taylor series for e to the t is as follows. So I'm going to put down at least 4 terms because that's what we're looking for. So e to the t, we should all know this. If you don't, well, go back to week 1. It's 1 plus t, watch me screw it up now, t squared over 2 plus t cubed over 3 factorial, and so on. Okay. That's where we're going to start, but I don't want e to the t. I want e to the minus t squared. So I'm going to replace the t by a minus t squared all the way across. So replace t by minus t squared. And if I sub that in for all of the different values here, I get e to the minus t squared equals 1. Okay, I'm replacing the t here, so I get minus t squared. The next one, if I put minus t squared in for t, it's getting squared away, so I end up getting plus t to the 4 over 2. And the next one, I'm going to get minus t to the 6 over 3 factorial. And it's going to go something like this. Yeah. And now I want to think of what to do next. What we want to do is, well, integrate this thing between 0 and x. Interesting, but that's what we're going to do. So integrate between 0 and x. We've done stuff like this. You've done it in first year calculus, very likely. And we can do the same thing here. That's going to give us this quantity on the left, the integral from minus t squared from 0 to x. And I want to think on the right of what this is going to look like. If I integrate all of these terms, I'm going to get t for the first one, right? I'm going to get t, and then it's going to be evaluated between 0 and x. I'm going to get an x at the end of the day. This term here, I'm going to get a minus t cubed over 3. And then I'm going to plug in the x minus, plug in the 0. And I get minus x cubed over 3. And then the next term, I'm going to integrate. I get t to the 5 over 5. 5 times 2 is 10. So I'm going to get t to the 5 over 10 evaluated between t equals 0 and t equals x. The 0 is nothing, so I get x to the 5 over 10. And we can do the same thing here. It looks like we're going to get a minus x to the 7 over, over, what is 3 factorial? 6. So x to the 7 over 7, or it's t to the 7 over 7, then we're subbing in an x, but I think it ends up being a 42. Yeah, and this could go onward. And we're almost there. The last thing we need to do to recreate this function is to multiply by that scaling factor. So we multiply by the 2 over root pi to finish things off, to seal the deal. And then we get that 2 over root pi times that integral. That's the same thing now. We've now created the error function of x is equal to 2 over root pi times that first one minus x cubed. It's a little bit awkward, but 2x cubed over 3 root pi maybe. You know what? I'm going to write that as a coefficient just to make things a little bit more elegant. And then let's see here. We're going to get a 2 over root pi is going to be 2 and 10 go together and give me a 1. So 1 over 5 root pi, I believe, x to the 5. And then finally, 2 over 42 gives me a 21 on the bottom. So I think we get minus 1 over 21 root pi x to the 7. And that's what we got. Funky, eh? So there you go. That is what looks like the first 4 terms of the Taylor series for this crazy function. So we can even find a Taylor series approximation centered at x equals 0 for our function. And that's really, really neat. I think it's very powerful, and it goes to show you not only can we find out properties about this function, we can also use a lot of the things that we know. We can also, talk about everyday things like Taylor series, about properties of integrals and so on, to gain all sorts of information about this interesting function. So the main purpose of this exploration is to get us familiar with the idea that special functions like these can still have useful properties that are in common with all sorts of functions that you might already be used to. Okay, so the simplest question still remains: how can we easily evaluate this function or other special functions like it? We have a function, we know how to do its Taylor series, we know how to do all these other things, and we know all sorts of observations about it, but how do I say, what is error function at 1? Well, the answer, we can't, but we can use approximating techniques. And that is the motivation for this section, is that because we have this function that's defined just in terms of an integral, maybe I don't have the ability to work with it directly, right? The error function evaluated at 1 is literally going to be, right, 2 over root pi times the integral from 0 to 1 of e to the minus t squared dt. But if I can't do this integral, how the heck do I ever figure out what the error function at 1 is? You know? The idea is that I have to find a way to approximate this integral. And it turns out that we can, using techniques that we know, using techniques that can be extended from things that we know, and some of it gets pretty powerful and pretty interesting. So hopefully that was interesting. I love that lecture because I think it, I don't know, I find it a little bit mind-blowing to think about this stuff. I never thought a lot about functions beyond the basics, right? Like in high school, you're exposed to roots and polynomials and exponentials and logs and sine and cosine and all of those. But there's a whole infinity of different kinds of functions outside of the ones that we can simply write down. So I think it's neat to talk about that. And then to frame this question about a numerical integration around functions like this, and that's why this is a useful technique. I just like it. I think it's a nice approach, and I hope that you found it fascinating as well. So we're going to start talking about some of those methods for numerical integration in the next lecture, and yeah, we're going to be putting down at least 3 lectures on this topic that will start with things that you know and extend to crazier topics that do a better and better job, as usual. So join me then. It should be fun. And until then, I wish you all a fond farewell. Bye for now.